Greetings and welcome to the lesson. Today we want to move to the cost estimation and interpretation chapter, which has 4 subtopics. Number 1, ordinary least squares method. Number 2, specifications, stock assumptions of ordinary least square. Number 3, we have the computer output and technical versus managerial interpretation of OLS results. Then lastly, we have the learning curve models and their application. So begin with the ordinary least square method. Ordinary least square method. Ordinary least square. Now, the ordinary least square is a statistical method used to estimate the unknown parameters of a linear model. So, first of all, it is a statistical method which we use to estimate unknown parameters of a linear model, regression model, linear regression model. And the ordinary least square method minimizes the sum of squared differences between the observed independent variable values and the predicted values. You understand? Observed dependent variables and the predictable or predicted values. So you may have a simple regression model according to what we have here, and a multiple predictor. So the first method, ordinary least squares, we may analyze two. We have the simple linear regression. Simple linear regression. Simple linear regression can be expressed, because it's a linear equation. It can be expressed as follows: y is equal to beta naught plus beta 1x minus error. All right, this is an expression of a simple linear regression model. Simple linear regression, okay, where y is, now this y, candidates, is the dependent variable. Dependent. Y is the dependent variable. That is to say, the variable which we want to predict. The variable which we want to predict. Because you are discussing candidates cost estimation. The variable which you want to estimate is what we are calling the dependent variable, and is represented by y, the variable which we would want to predict. And this x, candidates, represents the independent variable. Independent variable. This x is the independent variable. The independent variable, that is the variable used to predict y. In other words, the variable used to predict y, used to predict the dependent variable. So the variable y depends on the independent variable. All right, the variable that we use to predict y is the independent variable. Then we have beta naught. Beta naught. Beta, this is a Greek alphabet, the second alphabet of the Greek language. Beta naught, it is the intercept. Beta naught is the intercept. Beta naught is the intercept. What does that mean? It is the value of y when x is 0. The value of y when x is 0 is what we are referring to as the intercept, represented by beta naught. You understand? The value of y, which is the dependent variable, when this x is 0. That is the intercept. Then you have beta 1. Beta 1, this one here. What does it represent? Now, beta 1, candidates, beta 1 is the slope. Beta 1 is the slope. What do you mean by slope? That is now the change in y for a 1 unit change in x. That's the slope. Change in y for 1 unit change in x. Change in y for 1 unit change in x. Change in y for 1 unit change in x is the slope, which is represented by beta naught in the simple regression line, linear regression line. Y is equal to beta naught plus beta 1x plus e. All right, the error, this one here, what I'm calling e but it's not e, is the error term. This is the error, the error term, the error term. Okay, what is the error term? Now the error term is the difference between the observed y and the predicted y. The error term is the difference between the observed y and the predicted y. The difference between the observed y and the predicted. The difference between the observed y and the predicted y is the error term. So these are the inputs in the simple line regression under the ordinary least square method. First one is the ordinary least square method. So we can use these candidates to estimate coefficients estimating coefficients using the ordinary least square method. The ordinary least square estimates the coefficients of B naught and B or beta naught and beta 1. Or less, I repeat, estimates the coefficients of beta naught and beta y by minimizing the sum of squared residuals, the squares. Alright, by doing what? By minimizing the sum of squared residuals, squared residuals. Let me note it down. Another important point. What did I say? I said that OLS estimates the coefficients of beta naught and beta 1. Ordinary least square estimates the coefficients of beta naught and beta 1. By doing what? By minimizing the sum of squared residuals. By minimizing the sum of squared residuals, and the formula is y1 minus y bar, y1, the summation of y1 minus y bar. We get the squared residuals. This is the expected and this is the actual. We minimize the sum of the squared residuals. By this difference we square. This is where, let me go the whole hog, where y is observed value of the dependent variable for the observations, for the nth observations. Observed value, y is the observed value, and y bar, on the other hand, is the predicted value. It's predicted value. Y bar is the predicted value. It's the predicted value of the dependent variable. This is of the dependent variable. It's the predicted value of the dependent variable. And y is the observed value of the dependent variable. Now we did indicate that B naught is the intercept, which is the value of y when x is 0, and that represents the baseline value of the dependent variable when the independent variable is 0. We also did state that beta 1 is the slope which indicates the change in the dependent variable for 1 unit change in the independent variable. Please note that B naught is the intercept. It is the value of y when x is 0, and and beta 1 is the slope, which is the change in y for 1 unit change in x. Then that is the simple linear regression. That is the simple linear regression. Then you have the multiple linear regression. Multiple linear regression number 2. Multiple linear regression. Multiple linear regression. What the syllabus is calling the multiple predictors. Multiple predictors. So we only had one independent variable, but we may have a multiple linear regression where we have multiple independent variables. Here we have multiple independent variables, as opposed to the simple linear regression where there is only one. Understand? In a multiple linear regression, we have multiple independent variables to predict the dependent variable y. And the model is expressed as y being equal to beta naught plus beta 1 x1 plus beta 2 x2 and so on. So we have many other than just one independent variable. We may have one, we may have two independent variables, three independent variables. We can add here maybe beta 3 x3, like that. We may have 4. So there are multiple predictors to predict the independent variable y. You understand? Where y is the dependent variable. And of course, we must add, the error term at the end, where y is equal to the dependent variable. Y is the dependent variable. We have x1, x2, x3, x4, x5, depending on the number. These are the independent variables. Independent variables, x1, x2, x3, and so on. These are independent variables. Beta naught is the intercept. Beta naught is the intercept. This beta naught is the intercept. Beta naught is the intercept. Then we have beta 1, beta 2, beta 3, beta 4, beta 5. These are coefficients for each independent variable. Coefficients for each independent variable. You can see these are coefficients in this equation. So the ordinary least square, just as the simple linear regression, the ordinary least square method, the ordinary least square estimates the values of B naught, beta naught, beta naught, beta 1, beta 2, just like the linear, simple linear regression, by minimizing the sum of squared residuals. The sum of squared residuals. By minimizing the sum of squared residuals. That is the multiple predictors. And again, beta naught, just like the simple linear regression, represents the expected value of the dependent variable when all independent variables are 0. When all independent variables are 0. This beta naught. When all these independent variables are 0. So do you understand? Beta naught, I repeat, represents the expected value of the dependent variable y when all independent variables are 0. When all independent variables are 0. Because if you have 0 here, 0 here, 0, you only remain with beta naught. That's the interpretation. You understand? And then we have the coefficients. The coefficients. The coefficient beta 1, beta 2, beta 3. These are coefficients. Beta 1, beta 2, beta 3. These are coefficients which represents the change in the dependent variable for 1 unit of change in the corresponding independent variable, holding all other variables constant. Holding all other variables constant. So the coefficients beta 1, coefficients beta 1, beta 2, beta 3, and so on represent